double rotor system. This is an extension of single rotor system. Consider the case of crankshaft of a multi-cylinder engine to understand this. The firing order plays a major role in the torsion of the shaft. The equation of frequency here remains the same as that in single rotor system, that is 2 pi root Li by Cj. So this is the equation for time period. Now here the shaft is under the influence of two different rotors. So the inertia of both the rotors will affect the frequency of the shaft. To understand this, we'll give equal angular deflection to both the rotors but in opposite direction. It is observed that along the length of the shaft, there is a point where the torsional moment due to both the rotors is nullified. Hence, the rotation of material at that point is zero. That is, the shaft elements at that point do not rotate, or say they do not twist. This point is called node. We can try to observe that in the setup, and we can also calculate its distance theoretically. Say we have two rotors A and B, and they are mounted on a shaft, and the distance of node from rotor A is denoted by L subscript A. So now we can determine this length by balancing the torsional moment on both the sides. So that is LA into IA, length into I, that is inertia. So LA into IA is equals to LB into IB. Now if the total length of shaft is L, then LB can be denoted by L minus LA. So we can get the equation of LA as IB into L by IA plus IB. Now let's perform the experiment. This is a setup for two rotor systems. This rotor has diameter of 0.2 meters and its weight is 3.5 kgs, while the diameter of this rotor is 0.19 meters and its weight is 2.15 kgs. Now you see this thing? That's a collet. It is used to clamp this shaft. This shaft is made up of spring steel and its diameter is 3 mm. Now, in order to study the torsional vibration of the system, we need to give torsional deflection to both the rotors, but in opposite direction, and it has to be uniform in magnitude, or say equal in magnitude. So if this rotor is rotated by some angle in clockwise direction, the other one has to go in the anti-clockwise direction from the mean position. So if this is the mean position, or say the equilibrium position of the system, we'll have to deflect it like this, and then we leave it. And that's how we can measure the time for 10 oscillations. We'll perform this experiment for 3 or 4 times, and we'll record the time period for 10 oscillations, and based on that we'll move further with the observation and conclusion. Oh yes, and the distance between these two collets, so that is this end to this end, that is 0.86 meters. So that will be the length of this shaft. You can consider this as the whole system, this and this. So this is one rotor, this is another rotor, and this is the shaft. Giving it deflection in first direction, and this is the other. So this time was 5.51 seconds. We'll try it once more. This was 5.42 seconds. We need one more reading. And so this is 5.63. So we have got 5.63 seconds. So based on these three readings, we'll have our observation and conclusion. As seen in the experiment, we have obtained three values of time period. We average out these values to get the time period as 0.5520 seconds. Now to locate the node point, plug in the values in the equation and we'll get this as 0.5897. To verify this length, we can again go to the setup, perform the experiment, and we can try checking if the length is somewhere near this. So this was a study on torsional vibration of double rotor system.